We've been talking a lot about different strategies for finding the first and second derivative of functions, and then using that to infer different things about the behavior of the function and the graph of the function. Let's take a look at a couple examples. This first example is going to require a lot of work in making the derivative. So this video is just going to be me taking the derivative of that and simplifying it into a way that we can kind of make some sense of it. So here we are, we're on page 330 in the notes. And we're given the equation of the first derivative of some function. And we want to determine the intervals where the graph of g of x is concave up, concave down, and determine the x values of the points of inflection. All right, so in order to answer those questions, we need to find the second derivative of g. So we need to find the derivative of this. The first thing I'm going to do is I'm going to factor this a little bit. So this is negative 12x over x to the fourth plus 6x squared plus 9. That's a perfect square. And it'll just make our lives a little bit easier if we write that as x squared plus 3 quantity squared. All right, so this is a quotient, so we need to use the quotient rule for this. And so what I'm going to do is I'm going to break out the numerator and the denominator. I'm going to do this over here. So the numerator is equal to negative 12x. And so the derivative of the numerator is equal to negative 12. And the denominator of x is equal to, we said x squared plus 3 quantity squared. And so to find the derivative of that, we're going to use the chain rule. So that's 2 times x squared plus 3 times the derivative of x squared plus 3, which is 2x. And that is equal to 4x times x squared plus 3. And this doesn't look easier than just taking the derivative of this, but you're going to see the impact in just a few moments. So what we need to do is we need to use the quotient rule. And so the quotient rule says that the second derivative of g is equal to the derivative of the numerator times the denominator. So that's negative 12 times x squared plus 3 quantity squared minus the numerator times the derivative of the denominator. Negative 12x times 4x times x squared plus 3. And then all of that is over the square of the denominator, which is x squared plus 3. X squared plus 3 squared squared, which is x squared plus 3 to the fourth power. All right, and so that's kind of a mess like the quotient rule normally is, but let's do a quick thing first. We can notice that every term in the numerator has a factor of x squared plus 3. Here it is to the second power, here it is to the first power, and it's to the fourth power down here. So let's cancel out one factor of x squared plus 3 from everywhere we see it. So that's going to become 3. So that's g second derivative is equal to negative 12 times x squared plus 3. Okay, and then negative times negative 12x times 4x is going to be positive 48x squared over x squared plus 3 cubed. All right, and now we'll distribute that out. So that becomes negative 12x squared. Negative 12 times 3 is negative 36 plus 48x squared over x squared plus 3 quantity cubed. All right, and so let's combine our like terms. So 48x squared and negative 12x squared would be 36x squared minus 36 over x squared plus 3 quantity cubed. I'll factor out a 36 from here, so that becomes 36 times x squared minus 1 over x squared plus 3 quantity cubed. And the last thing I do is, why don't I factor this? Because x squared minus 1, that's the difference of two squares. So that's just x plus 1 times x minus 1 over x squared plus 3 quantity cubed. All right, so that was a lot, but this is a nice format for us to answer the second part of our question, which is going to be using this and analyzing this function to find the concave up, concave down, and points of inflection. So hang on, and we will do all this in the next video.